Well, hello everybody. Right now we're going to review how to operate with radicals and how to solve radical equations. If you take a look at the notes that you have here, there are some properties of radicals we want to make sure we talk about. If you have a radical, I'm going to scroll this up for a second, some terms here. This thing here called the index, and whatever's underneath the radical sign is your radicand. So if you have an index and your radicand is raised to a power that equals the index, that cancels each other out and you have just the radicand left. Also, if you have a radicand that can be factored into a couple different factors, you can rewrite this, give it its own radical sign, make sure you keep the index on each the same. And similarly, if you have a fraction under a radical sign, you can separate it out, give the numerator its own radical, again keep the same index, give the denominator its own radical. Alright, having said that, we're going to take a look at some simplifying of these radicals. I'm not going to go through each of these examples. These are things that you can take a look at on your own, things that you want to make sure you are aware of, however. If your index is, say, a 3, you are looking for perfect cube factors to be underneath your radical sign. So perfect cube numbers include 8, and actually over here we've got a list for you of some typical perfect cube numbers and variables, things you might want to look over. So you want to make sure if your index is some number other than 2, you're looking for perfect either cubes or things to the fourth power depending on what that index is. Alright, so just a reminder on that, you can go back through, look at the notes on how to do these simplifications. We are going to move on and make sure we talk about how to do some math operations when we have radicals. Alright, when we are adding radicals, we need to make sure we are adding like radicals. That means that if they are like, the index is the same and the radicand is the same. When we combine like radicals, then we are just combining the coefficients of our like radicals. First thing you want to do though is make sure you simplify each radical term as much as you can. So if you were to take, for example, radical 12 and simplify it, that would simplify to 2 radical 3. This term here, 9 radical 1/3, that would simplify to 3 radical 3. That's one that I'll take you through just over here on the side. If you have 9 multiplied by radical 1/3, I'm going to break this radical 1/3 up and give the numerator its own radical and the denominator its own radical. Keep in mind though, I'm multiplying 9 times this. So radical 1 over radical 3. Radical 1 is the same thing as 1. Square root of 1 is 1. But I have this radical 3 in the denominator. I'm going to need to rationalize that. So I'm going to multiply by radical 3 over radical 3. That's equivalent to 1, so I'm really not changing the value here. This is going to be equal to 9 times radical 3 over 3. Now, 9 divided by 3, this part here can be simplified, leaves us with 3 radical 3. So that's why back in our original equation, when they simplified 9 times radical 1 over 3, they got 3 radical 3. So if I continue on, and I'm assuming that these are all simplified correctly, I'm looking for like radicals. Let's see if I can erase this here so that we can see a little bit better. I'm looking for like radicals. That means the index is the same and the radicand, the number under the radical sign, is the same. This first one, radical 3, that's a like term to this radical 3, so I can combine them. 2 of these plus 3 of these gives us 5 of these radical 3's. And then I look at the next terms. I have radical 2 here and a radical 2 here. Those are like terms. So I can take my two radical 2's and subtract 6 of them, giving us this negative 4 radical 2. So that's how we can add and subtract. We've got to make sure we have like radicals. Multiplying, a little bit easier. All I have to do is make sure I have my like radicals. And if there are coefficients or numbers out in front of the radicals, I multiply those. And I put that product in front of a radical. And then whatever is underneath the radical sign, or the radicands, I can multiply those together and keep them as a radicand. Now, I would then have to make sure that I simplify the radicals afterwards. Each of these is an example. You can go through those on your own. We're going to be seeing more of this in the examples that are coming up. So I'm going to go ahead, go to the next page. You have the notes though if you need to go back and look at these examples. They are written out for you. Alright, so I'm going to the next page. What I want to make sure is that if I have a fraction, get my pen back here, try again. If I have a fraction and there's a radical in the denominator, I cannot leave it like that. I need to do what's called rationalizing this denominator. That means getting rid of that radical in the denominator. Most of you have shown me that you remember how to do that, so I'm just going to go straight to some examples here. Starting with this one where I have 2 over radical 7. Problem is, radical 7 is in the denominator. We can't leave it there. So we're going to multiply this by radical 7 over radical 7. That way, in the numerator, I'm going to have this 2 times radical 7. The denominator, remember, I'm multiplying. We've got the same index. I'm going to multiply the 7 times 7 and get 49, which is perfect square, so I'm going to simplify that. And that denominator becomes just a 7. Nothing more I can simplify, so I'm finished with this one. But always make sure you check to see if you can simplify further. If you leave something in a form where it is not fully simplified or reduced, you will lose some credit. All right, we're going to go to the next example here. I have 5 over radical 8. Now this radical 8 is not in its simplest form. But most of you would say, okay, I'm going to go and multiply this by radical 8 over radical 8. That's a multiply there. If I do that though, I'm going to have extra steps with my fraction when I'm going to have to do some more simplifying. So what would be better is if I went ahead and instead of multiplying by radical 8 over radical 8, multiply this 8 by a radical that will give me a perfect square number in the denominator. For example, 8 times 2 will give me 16, and 16 is a perfect square. So if I multiply this by a radical 2 over radical 2 instead, then I, as in this example here, will end up with 5 radical 2 in my numerator and a radical 16 in the denominator, which will simplify to 5 radical 2 over 4. And I've taken care of the problem of the radical in the denominator. So easier step on this one, not multiplying by radical 8, but multiplying by radical 2. Alright, that brings us to this next example, and this time I do not have square roots, I have cubed roots. So I want to multiply my denominator by something that will give me a perfect cube. So what I want is a radicand that is equal to a perfect cube. In this case, I can multiply 9 times 3 to get 27, and 27 is a perfect cube. So I'm multiplying top and bottom by cubed root of 3. That gives me 4 times cubed root of 3 in the numerator and the cubed root of 27 in the denominator, which simplifies to 3 here. Nothing left to simplify on that, so that one is finished. So, hint on here. You want to multiply the radicand by whatever gives you the smallest possible value that you can simplify in the denominator. Alright, let's move on then. What happens if we have more than one term in our denominator and we still have a radical? Like this case, we would need to multiply by the conjugate of that denominator. Conjugate is same term to begin with, same term ending, but change the sign in between the two terms. So I'm going to multiply this by 5 minus radical 3. My numerator has to be exactly the same. I'm going to put parentheses around these because it's a binomial. And this is going to give me 2 times the binomial, 5 minus radical 3, all over. If you want to use the box to multiply these two binomials, you can go ahead and do that. I'm going to erase this so that we can see what we're doing here. So I'm multiplying 5 and a positive radical 3 by 5 and a negative radical 3, which will leave me with these terms here. Positive times a negative gives me a negative. Radical 3 times radical 3 gives me 3. So I'm going to put these terms together. When I multiply by conjugates, my middle terms cancel each other out. So these are going to cancel, and I'm going to have 25 minus 3, or 22 in my denominator. This fraction I can simplify. 2 goes into both of these, and that leaves me with 5 minus radical 3 all over 11. Now notice in this example, when I had that numerator of 2 times 5 minus radical 3, I did not distribute. The reason I didn't do that is because I want to wait until the end to see if I can cancel out any factors, and in this example I did. So best not to distribute or wait to distribute in case we can simplify by canceling common factors in the numerator and in the denominator. Okay then, let's take a look at this next example. This time we've got a binomial in the numerator and in the denominator. But I still have this problem of this radical in the denominator, which is not allowed. So I still need to multiply by conjugates, but it's got to be the conjugate of the denominator. And I'm multiplying same in the numerator. Alright, I'm going to throw parentheses around these so that I make sure that I do the multiplication correctly here and distribute all of this. I'm going to create a couple boxes here. Help me make sure that I do this multiplication correctly. So I'm multiplying 2 plus a radical 5 times a 4 plus a radical 5. This is the numerator. Gives me 8 plus 4 radical 5 plus 2 radical 5. These two now are like terms because they're both radical 5s. And then I have a positive times a positive, gives me a positive, Radical 5 times radical 5 gives me 5. So I'm going to have now 3 terms in my numerator. Actually, no, I'm going to have 2 terms. I can combine my 8 and 5, gives me 13. And then I have like terms that I can combine. My 2 radical 5 and my 4 radical 5 give me 6 radical 5. In the denominator, I'm going to be multiplying conjugates. 4 minus radical 5 and 4 plus radical 5, leaving me with 16. These two terms are going to cancel each other out, and a negative times a positive gives me a negative. Radical 5 times radical 5 gives me 5. So these two terms cancel out, and I have 16 minus 5, which is 11. Nothing left to simplify in this one, so there's my final answer. Alright, some hints to know that you have simplified. You can read through those on your own. We're going to move now to how do we solve radical equations. Now, solving equations requires a few steps, including checking our answers, but let's first make sure that we know what an equation looks like. If it's a radical equation, it means that I have a radical with a variable under my radical sign, or a variable as a radicand. So this first equation here with my radical x, this qualifies as a radical equation. Over here though, I have a radical, but my radicand is a number, it's a constant and not a variable. So if I have no variable here, this is not a radical equation. Alright, so now we know what a radical equation is. Let's go ahead and look at some examples in solving them. Steps are written out for you here. First thing I want to do is isolate my radical, get it by itself. And then I want to square both sides of my equation, entire sides. So if I have a radical on one side, isolated nicely, no matter how many terms I have on the other side, let's say I have, remember terms are separated by pluses and minuses. Let's say I have 2 terms on this other side. The entire side, everything there gets squared. Not individual terms, but the entire side, or the entire polynomial. Alright, once we do that, then we go ahead and solve for our variable. We must make sure we check our solutions because we might have some extraneous solutions. And I'm going to show you more than just checking algebraically. We're going to look at also checking graphically. If we have an equation where there is more than one radical, then we will actually have to do these steps more than one time, and we'll see an example like that shortly. Let's move on right now. Let's take a look at this first example, number 1. I want to find my radical. Here's the radical. And here's my equal sign. Now I have this 5 on the same side as my radical. I need to have just the radical by itself, so I need to subtract 5 from both sides, which leaves me with radical 2x minus 1 equaling a negative 3. Now that I have my radical all by itself, I take this whole side and square it. Take this side also and square it. By doing that, I end up with 2x minus 1 by itself on the left. And a negative 3 squared is a negative 3 times a negative 3, gives me 9. Add 1 to both sides. 2x equals 10. And divide by 2, and I get x equals 5. Now, I need to check this answer. And I think you all know how to check algebraically. Substitute in the value of 5 for x in the original equation. So to do an algebraic check, I would go back to my original equation, put in 5 for x, and then solve that and see if the left side is equal to the right side. But I want to show you a graphical way to check. Here's what I would do if I'm going to check graphically. I'm going to go back to my original equation. Everything on the left-hand side, get my pen back here, everything on the left-hand side, I want to enter into my calculator and graph it. So I could put this in my f1 of x if I'm using an Inspire, or into y1 if I'm using an 83 or 84. Then everything on the other side of my equation, I want to put in and graph as a second function, or y2, in my calculator. So down here we've got a picture of a graph, and this first function here, that's my square root function. So this would be the radical 2x minus 1 and plus 5. Now notice we're adding 5. It's not underneath the radical sign, which really makes this a vertical shift up 5 units. And you can see where this thing is starting up here at 5. The other side, my y equals 2, is this line right here. Well, excuse me, that's my x-axis. Here is f of x equals 2, or y equals 2. Notice these two graphs do not intersect anywhere. So if there's no intersection point, then there's no solution, which means that my solution of x equals 5 is an extraneous solution. So this is an extraneous solution, which is what I should find if I were to do my algebraic check. So let's just finish up this algebraic check and make sure I also get extraneous solution for that. Under this radical, I would have 10 minus 1, and then I'm adding 5. We want that to equal 2 if I have a true solution. This becomes radical 9 plus 5. This becomes 3 plus 5, and I think you can see at this point this does not equal 2, which again supports the fact that I have an extraneous solution. So you can check either algebraically or you can check graphically. Let's take a look at another example here. I have radical here, nothing on the same side as the equal sign, so I can just go ahead and square both sides. On the left side, I've got a binomial here, so I need to make sure that I square the binomial. You can either use the box or whatever method you like. Should end up with a trinomial here. We're going to get x squared minus 2x plus 1 equals 5x minus 9 after we square both sides. Now, I have a quadratic equation here. I know that because I have this squared here. My highest power is 2. It's quadratic. And to solve a quadratic, I need to move everything to one side. So I'm going to subtract the 5x, add the 9, and then see if I can solve this thing either by using the quadratic formula or by factoring. Okay, looking at this, I think I can factor this. I'm looking for two numbers that are going to multiply to a positive 10, add up to a negative 7. I think minus 5 and minus 2 will work for us. So I get x minus 5, x minus 2 equals 0. Set each factor equal to 0 and solve, and I get x equals 5, x equals 2. Two solutions. If you were to check this graphically, you would see two intersection points. There's one there where x is 5, and there's one here where x is 2, which means both of my solutions are valid. 2 and 5 are solutions. All right, let's look at another one. Looks like I have two radicals, but they each are on their own side of my equation, so I can go ahead and just square both sides. This becomes 2 times 4, 2 gives me 4, and this is multiplied times x plus 8. That will equal 3 times 3. I think that's a 3. Yep, that is a 3. 3 times 3, or 9, times x minus 2. So I'm going to go ahead and distribute here. This is a linear equation because my x has a power of 1, makes it linear, so I need to get x's on one side, all numbers on the other. I'm going to subtract 4x from both sides and add 18 to both sides. 50 equals 5x. And 10 equals x. Do a check on that. I'm showing you here an algebraic check. And it looks like the left side comes out equaling the right side, so we have a valid solution. Put that in set notation, and we're all set. Okay, one more example here. This is an example where we have two radicals on the same side of the equation. So I want to isolate them, get them on their own side of an equation, and then square both sides. But because I have two radicals, I'm going to need to go through the process twice. So first thing I want to do, check for which one is the radical with the most terms underneath the radical sign. That would be this term. So that's the one that I want to start with getting by itself. So because I like to work with positives, I'm going to add this to both sides, essentially moving it over to the right. And the 3 that's already there, I'm going to subtract. So I'm going to end up with this. And on this side, x minus 3. All right, now I'm going to square both sides. Now remember, I take every term together as a side. See if I can get this to look better. Every term on the left here, two terms, I'm going to square that as a binomial. So on the right side, I'm just going to have x minus 3. But on the left side, I've got to take radical 3x minus 3 and multiply that by radical 3x minus 3. All right, this gives me 3x here minus 3 radical 3x, another minus 3 radical 3x, and then a plus 9. So I am getting a trinomial that looks like 3x minus 6 of these radical 3x's plus 9. All that is going to be equal to x minus 3. So now I've still got a radical, so I need to isolate that radical, which means I'm going to subtract 9 from both sides, and I'm going to subtract 3x from both sides. This leaves me with negative 6 radical 3x equaling x minus 3x gives me a negative 2x minus 12. Now I'm going to do the square each side again, which leaves me with, I'm going to start back here up at the top, give myself some space. Okay, so squaring the left side leaves me with 36 multiplied by 3x equaling, and I need to do this binomial multiplication. So you can create a box again to multiply these two terms. I'm going to skip over to what I know that equals and write that as 4x squared plus 24x plus another 24x gives me a total of plus 48x plus 144. Now again, I've got a binomial. I know that because x squared is my highest term, so I'm going to move everything to one side, set it equal to 0. So I'm subtracting what I get when I multiply 36 times 3x, and that is 108x. So I'm going to subtract that from both sides, and I'm going to get 4x squared minus 60x plus 144. And I need to solve this. So I think I'm going to be able to factor, but I'm going to take out my GCF of 4. And I can divide every term by that. I have an equation, so I don't need to keep that GCF. I get x squared minus 60 over 4 is 15 plus 144 divided by 4 is 36. This is factorable to x minus 12, x plus 3, x minus 3. I'm going to set each of those binomials equal to 0. Gives me solutions of x equals 12 and x equals 3. And I need to check these. And I'm going to leave that to you to check to determine whether or not those are extraneous solutions or valid solutions. Alright, so one last thing I want to make sure we know how to do, and that is how to change radicals back and forth to exponents. So let's say that I have a radicand raised to a power of p. I'm going to rewrite that as a radical, as an exponent. The k is my radicand. It's still being raised to the p power, but I have this index here, which can be written as an exponent and a denominator. So nth root of radical k to the p power equals k to the p over n. So let's just go through and rewrite these three examples and we'll be done. Alright, example 1. I have an index of 4, which means it can be treated as an exponent of 1 over 4. So I can take everything under my radical sign, this entire thing is being raised to the equivalent of the 1/4 power. Now remember, if something's in parentheses being raised to a power, each term inside the parentheses gets raised to that power. So this is equivalent to 16 to the 1/4, a to the 6 times 1/4 or 6/4, b to the 4 times 1/4 or 4/4. Now, of course, we can simplify this. 16 to the 1/4 is 2. A to the 6/4 I can simplify to be 3 over 2. B to the first power, or just b. Now, you might also see this written as a radical sign, where I have my a to the 3/2. Here's how that would work. This would be equal to, I'm going to break this a to the 3/2 down because 3/2 is the same as 1/2. I can write it as a to the 1 times a to the 1/2, b to the 1. This is really square root of a, so you might see this looking like this. 2 times a times b times the square root of a. That's a possibility, or this is a possibility for ways that you might see these. Let's look at this next example, number 2. I have an equation here, and I have 0.094 times a to the third, but under a radical sign. So this radical sign here, with an index of 2, I'm going to rewrite as an exponent. A to the third is being raised to the 1/2 power when it's a square root of 2. So can also be written as a to the 3/2 power. Alright, we could simplify it more like we did in example 1, but we don't need to do it twice, so now we're going to move on to this next example. Negative exponents can be written as positive exponents by putting them from numerators into denominators or from denominators into numerators. This was a numerator, so I'm going to make it now a denominator, which means I have 1 over that amount. Now, I am going to take my square root sign here, and I'm going to make that into an exponent. So this would be equal to 1 over a squared b to the 1/2, all to the 1/2 power. And then I'm going to take everything inside the parentheses and raise it to the 1/2 power. So I'm going to get a to the 2 times 1/2, which becomes first power, b to the 1/2 times 1/2, which is the 1/4 power. So you might see an answer written like that. Or, don't forget, this 1/4 power is the same thing as fourth root, so you also might see it as 1 over a times the fourth root of b. Both of these are possibilities for how that might be expressed. Alright, that'll do it for this evening, and we'll see you in class tomorrow. Thanks for listening. Bye.